So in this video, we are going to revisit the notion of what kind of payoffs are possible in equilibrium, where we have refined the notion of equilibrium to be subgame perfect Nash equilibrium rather than just a simple Nash equilibrium. And holding the payoff matrix the same, remember it looks something like this: 2, 2, 0, 3, 3, 0, 1, 1, C, T, C, D. This blue diamond showed you the set of feasible payoffs, and this green area showed you what's feasible as a Nash equilibrium. And you could pick anything such that it's greater than 1 for both players. And then there would be some sequence, B1, B2, B3, and so on, of outcomes of the combinations of both their strategies, their strategy profiles, which generate those outcomes, such that you could sustain this kind of payoff. And if both players play this strategy where after a given history, you're only continuing with this strategy that gives you an average payoff of this, if the other player has played that strategy so far, if that is the case and you're playing D otherwise, then this is a Nash equilibrium. The question is it also subgame perfect? And, well, yes, it is. And the reason is that there are only two types of histories here. One where players have cooperated so far, and the other where players have not cooperated so far. The key difference from what we learned earlier was that earlier you cooperated as long as the other player has cooperated so far. Actually, J subscript here makes sense. Now you cooperate only when both of you have cooperated so far and you deviate otherwise. And this is subgame perfect. Because if you have cooperated so far, then you can do no better than cooperating in the future. Because if you cooperate, you get this higher amount of payoff on average, higher discounted average payoff. If you don't cooperate, you get 1. If, on the other hand, you're in a situation where one of you has ever, you or the other person, has ever not cooperated, not followed this strategy profile, then you're already in a situation where both of you are always defecting, and since that's the Nash equilibrium of this one-shot game, of the game, if you play it just for one period, and since in the future both players are always going to deviate, then at no point do you benefit from deviating. So, to summarize, even if you refine the notion of equilibrium to be subgame perfect equilibrium rather than the Nash equilibrium, the set of feasible payoffs looks exactly the same. What you do need to modify is the strategy such that you only cooperate if both of you have cooperated so far rather than just the other person. And that brings us to a very similar notion of a Folk theorem, what we discussed earlier in the case of a Nash equilibrium, that we can show these 3 properties. One is that for any discount factor, if you have a subgame perfect equilibrium with these payoffs, with this payoff matrix, and with this game being played an infinite number of times, if you have a subgame perfect equilibrium, then it has to be that both players have an average discounted payoff of at least $1, of at least $1 each. The second property that this implies is that if you pick anything within this green shaded region, that's strictly more than 1 for both players, then you can find a discount factor such that you can find strategies to be able to sustain that average discounted payoff from this. So let's say you pick 1.1 and 2, you'll be able to sustain that as a subgame perfect equilibrium. You can find strategies to be able to sustain that and a discount factor to be able to sustain that. And the last thing is that you still always have the outcome DD being played all the time. You can have that be a subgame perfect equilibrium. Because if everybody is playing defect all the time, if both players are playing defect all the time, then neither player can profitably deviate in any period of this game. So by using the, what was it, one deviation property, you can show that there's a subgame, that playing DD always is a subgame perfect equilibrium. Because if both players are playing DD always, then there's no one deviation that's ever profitable. And so that concludes chapter 14. And see you during the Zoom meetings tomorrow.